All right, so we're going to talk about section 1.3, general problem solving. And we'll just scratch the surface of some of the type of examples that's in your book. There's many, many more in your book you can look over. But just in general, some typical problems you might see in your homework. So we first of all start out with this George Polya idea that comes from some solving guidelines that he set forth, and they seem kind of like, well, duh, these seems like what everybody would do, but sometimes you need to hear this, and that is number one thing whenever you're going to solve a problem is try to take some time, understand the problem, read it at least twice. And I find my students don't like to do this. A lot of times they see it's a reading problem, like, I hate reading problems. Me too, really, to be honest, because they're always going to be harder. You're going to have to think more, but that's really why we do math, is to try to be able to problem solve. So, we got to do this. But anyway, if you can just get past this first step, take some time, take a deep breath, and just say, hey, I think I can do this. Let's try to break this down. Read it carefully, read it twice, read it 3 times, read it until you feel like you get a handle on it. Determine what you need to know in the problem. For me, I'm a visual learner. A lot of times a sketch helps me. If there's a house or a car or a person in the problem, I'll sketch that out and kind of just get my brain kind of thinking around the problem. So I encourage you to do that, and then label any information. So that's big. That's step 1. And again, if you're following along in the notes, just reading from the notes that you have here as well. 2, devise a plan. Have you seen a similar problem? Sometimes it may look like something you've done before and you can emulate that. Do you know of any formulas that apply? Sometimes it's a geometry example and there's a formula. If it's a rectangle and they're talking about the distance around the rectangle, sometimes there's a formula. Or if it's a circle, or if it's asking about the area of the circle. So sometimes there's a formula. Distance equals rate times time. Could be anything like that. You may need to look up a formula. Next, is there an algebraic equation that could explain the question? Could you write an algebra problem from it? Are there patterns? Can you substitute easier or smaller numbers to see if you can do it in your head? Sometimes you know how to do the problem. You've done it 1,000 times in an easier version, so you can simplify the numbers and kind of emulate that to figure out, is it multiply or divide? What's the operation? So, for example, I know that if I spend $10 on 5 things, I spend an average of $2 on each. So it kind of tells my brain, hey, this is a division question. 10 items, 5 things, $2 each. So if I'm asked such a question as, with large numbers, 510,567.98 spent on 7.9 things, I get kind of jumbled up in the larger numbers. And if I can think, hey, this is just the same old thing. It's the same thing. Just divide those. I just need to divide those numbers. Same idea. So sometimes substituting easier numbers is a good strategy. Then 3, carry out your plan. That's getting past 1 and 2 is the hardest part, right? Then carry out the plans. And 4, we should always check our results. Use your estimation techniques to ensure that the answer seems reasonable. Sometimes if you went the wrong way with the if it was supposed to be divide and you multiply, if you think about it, then you can tell, hey, this doesn't make sense. I know in real life that wouldn't work. So see if the answer makes sense. Check that out. All right, now another type of reading problem that you might encounter is a proportion. So we're going to talk about proportions here in problem solving. Proportion is a statement of equality between 2 ratios. Like A is to B as C is to D, or A over B is equal to C over D. That's called a proportion. Anytime you have 2 fractions or 2 ratios set equal to each other, it is true that the cross products are always equal. It's a neat thing. So this A times D has to be equal to B times C, or C times B, either way you want to say it. But the cross products are always equal in a proportion. Some examples of things that are proportional would be like recipes. If it calls for 2 teaspoons for 4 servings, then how many teaspoons for 9 servings? That should be a proportional thing in recipes usually. 3 teaspoons of weed killer for 2 gallons of water. So how many teaspoons for 3 gallons of water? So these things should be proportional amounts. 1 part vinegar to 1 part oil and 10 parts water. Can you double or triple this mix? And how about $5 for 9 gallons of gas? So how much for 10 gallons of gas? Those should be proportional. All right, here's an example. 2-cycle engine oil is used for weed eaters, chainsaws, etc. Maybe you've had to do this in your life. It may call for a 32-to-1 ratio of gasoline to engine oil. This means 32 ounces of gasoline to 1 ounce of engine oil. It may be easier to think of this as 120 ounces, which is the same thing as a gallon. We usually buy our gas in gallons, so that might be easier, to 4 ounces of engine oil. Okay, so here's some sample ratios. If I write that as 32 ounces of gasoline, takes 1 ounce of this 2-cycle engine oil. Then if I have 128 ounces of gasoline, how many ounces of oil? And I've kind of given that one away again, but I just wanted to prove to you that this works. So if we write up something we know is proportional, that we know is supposed to be a 32-to-1 ratio for this gasoline to oil, then we could put in anything here, however many ounces of gasoline we buy. We could do it anyway, but it's a 32-to-1 gas to oil. So over here we just need to have gas compared to oil as well. We need to have it set up the same way. So we could leave either one of these unknown actually. Then you can leave off these units once you get it all set up. It's really just saying 32 is to 1 as 128 is to 1, as long as you have it set up correctly. Then you can cross multiply. 32 times x is 32x, and 1 times 128 is 128. And then the algebra step for this is you divide by what's with your variable, divide by what's with your x. On each side, dividing that off leaves 1x equals 128 divided by 32, which is your 4. So 4 ounces of oil. If you got the whole gallon thing going on there, it's going to take the 4 ounces of the 2-cycle engine oil. All right, so now I have another example for you below. We can use this strategy for many, many things. So what if you bought 3.5 gallons of gas? How much oil are you going to need to put in that? So now we know, and you can use any ratio you like, but I'm going to go with the 1 gallon. That was the 128 ounces of oil, of gas, sorry. 128 ounces is the same as 1 gallon of gas. Takes 4 ounces, as we saw above. So if we bought 3.5 gallons of gas, how much oil are we going to have to put in that? And there's other ways to do this. You might be saying you kind of just know the unit measure there, but this is kind of leading up into using proportions. So go with me here. So we got our gallons over ounces, and that's how you want it to be in your proportion, comparing like things. If this be a true ratio, 1 gallon of gas takes 4 ounces of engine oil, then 3.5 in gallons takes how many ounces of engine oil? So again, gallons to ounce should always work it out to where then we can use this proportion idea. And you can kind of ignore the units once you get it set up. 1 is to 4 is 3.5 is to x is really what we're working. Then you can cross multiply. 1 times x is 1x, or just x. And then 4 times 3.5, let's see, is that 14? So x then would be 14. So that solves our question. That takes 14 ounces of our 2-cycle engine oil. All right, so then I have an activity. So again, pause the video anytime we get to the activities to practice these. I'll go ahead and keep rolling though, so you'll have the answers to compare your work to. So it says how many ounces will we need for 2.2 gallons of gasoline. So I know 1 gallon is 4 ounces of the 2-cycle engine oil. So 2.2 gallons is how many ounces? That would be my ratio I'm setting up. Then I would cross multiply. I would have 1x equals 4 times 2.2. So your answer there should have been 8.8 ounces. The next activity 2, we do the weed killer. A ratio for weed killer calls for 5 ounces to 1.2 in acres. So when I write my proportion, this should be ounces to acres as well. So it says how many ounces for 4 acres. So I've got acres is known, 4 acres, that goes on the bottom, and I don't know the ounces. Again, ounces to acres, comparing like things there to set up your proportion. Once you get it set up right, again, you can ignore these units. So we really got 5 is to 1.2 as x is to 4. Then we do our cross multiplying. 5 times 4 is 20. 1.2 times x. Oh, look, my x is on the right side. That's really okay. Just remember, you always divide by what's by your x. So we're dividing out the 1.2. That leaves 1x equals, I don't know that in my head, so I'm going to use my handy-dandy calculator. It'll be 20 divided by 1.2, which is 16.6 repeating. So about 16.6 is what you should have, and that will be in what ounces? X ounces I was trying to figure out. All right, the next one will be a medical example with insulin. So let's read through that. Insulin comes in vials labeled with the number of insulin units per cubic centimeter, or cc's of fluid. An insulin vial labeled U40 has 40 insulin units per cc's of fluid. Tyler's insulin dosage is 30 insulin units. So how many cc's are needed for Tyler? So we know 40 units in the reading. 40 units is 1 cc, and Tyler needs 30 units. So this is what it comes in, and Tyler only needs 30 of that. So we know how many cc's should we give Tyler. So units to cc's, just make sure you got it set up correctly in the right order. So 40 is to 1, is 30 is to what? It gives us a nice proportion, so we can cross multiply. 40x equals 1 times 30. And then we divide that out on each side to get x equals in 0.75. So we're going to give him 0.75, and that's in x cc's is what we were solving for. He should get 0.75 cc's. And then I have some activities for you to do there. Again, pause the video to practice that. I'll keep rolling. On number 3, we know 40 units per 1 cc. And so this patient needs 70 units. So let's see, 70 units is how many cc's? So that's 40 is to 1, as 70 is to x. You will then cross multiply and have 40 times x equals 1 times 70. Divide out the 40. And that will be, let's see, 70 divided by 40. Your answer there should have been 1.75 in cc's. Okay, the next example goes a little different and mixes it up on us. And we've got 40, our base thing, 40 units is a cc. And this could be different depending on the directions, but in our direction it said 40 units is a cc. And then it says 7 cc. So they told me this part and didn't tell me how many units it was. So it left that part out instead. But that's okay, same idea. We've just got units over cc, units over cc's, and then drop all that out, and 40 times 7 is 280. 1 times x, 1x, so x is 280 units for that, 280 units. Another application of this, probably the last one we get through on this video, is shadows. As a matter of fact, I think I'll go ahead and pause it so that I can finish this out on the next one. I can only do 15-minute videos on this YouTube channel, so I always have to abruptly kind of stop this. So I'm going to go ahead and stop here, so I'll continue this on a next video. See you in a second.